How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You're staring at a blank screen. A blinking cursor mocks you from the corner of a document. You need an idea, a starting point, a spark. So you open another tab and type a simple request into one of the new generative AI tools. Something like, write a short poem about the loneliness of a lighthouse in the style of Edgar Allan Poe. You hit enter, and for a fraction of a second, nothing happens. It's a tiny, almost imperceptible pause. But in that pause, an act of creation is occurring on a scale that is difficult to comprehend. Then the words begin to flow onto the screen, not typed, but manifested. Upon a crag of endless night, a solitary cyclops gleams. It begins. The language is perfect. The cadence, the mood, the word choice. It's not just a pastiche. It has a flicker of something more. In less than 10 seconds, you have a complete, evocative, and eerily beautiful piece of original verse. You can change a word, ask for a different ending, or tell it to make the lighthouse a character in a space opera. It complies instantly. It feels like magic. It feels like talking to an imagination that is boundless and instantaneous. We've all had a moment like this in the last few years. Whether it's generating an image of an astronaut riding a horse on the moon, getting a complex coding problem solved in seconds, or having a chatbot explain quantum mechanics to you like you're a 5-year-old, we are living with a new kind of magic. And we tend to explain this magic to ourselves using the one analogy we have for intelligence, the human brain. We even call the underlying technology neural networks. We imagine these systems are thinking, that they are structured like our own minds, with digital neurons firing in some silicon skull. But have you ever stopped to wonder how that actually works? What is happening in that brief pause between your request and the AI's response? If we were to trace the signal from your keyboard out into the world and back, what would we find? What are the fundamental rules, the first principles, that make this new magic possible? Because what if I told you that our common assumption is wrong? What if I told you that the computers running these incredible neural networks don't work like brains at all? In fact, they work in a way that is almost the complete opposite. And that fundamental difference is leading us toward a hidden crisis, a global power crunch created by our insatiable demand for this new magic. Today, we are opening a black box that very few people ever think about. It's not the AI software itself, but the physical machine it runs on. We're going to deconstruct the very idea of a computer and ask a radical question. What if we stopped trying to simulate a brain with software, and instead we tried to build one in hardware? This is the story of neuromorphic computing. To really understand the miracle of modern AI, you have to appreciate its seamlessness. It's woven into the fabric of our digital lives so perfectly that we often don't even notice it. Think about your day so far. When you unlocked your phone with your face, and AI analyzed the geometry of your features. When you scrolled through your social media feed, and AI curated the content, predicting what would make you pause, what would make you laugh, what would make you angry. When you navigated to work, an AI calculated the fastest route, processing real-time traffic data from thousands of other users. It recommends your music, filters your spam, translates your conversations, and tags your friends in photos. This intelligence is ambient. It's all around us, working silently in the background. And now, with generative AI, it has stepped into the foreground. It has become a creative partner, a research assistant, a tireless brainstorming tool. It can write legal contracts, design architectural plans, and even create music that can move you to tears. The sheer capability is staggering. It feels like we have bottled lightning. It feels like we have finally created a machine that can think. And that word, think, is where our intuition leads us astray, because we associate thinking with the one object we know that does it best, the human brain. The brain is a masterpiece of efficiency. It weighs about 3 pounds, fits inside your skull, and runs on about 20 watts of power. 20 watts. That's less power than it takes to run a dim light bulb. With that meager energy budget, your brain performs feats that the world's most powerful supercomputers still struggle with. It can instantly recognize a friend's face in a crowded room, a task that requires immense parallel processing. It can learn a new language, compose a symphony, or navigate a complex social situation. It does all of this while simultaneously regulating your heartbeat, your breathing, and a million other subconscious processes that keep you alive. So, when we see an AI generate a beautiful poem, it's natural to assume that the machine behind it must be operating on similar principles. We imagine a vast, interconnected network, a silicon brain humming away in a data center somewhere, processing information with the same beautiful efficiency as the neural networks in our own heads. The name itself, neural network, encourages this comparison. It suggests a system of artificial neurons and synapses, learning and adapting, making connections, and achieving a kind of digital consciousness. This is the magic we see, a powerful, efficient brain-like intelligence. But the reality, the architecture that underpins this entire revolution, is built on a blueprint that is profoundly, fundamentally not like a brain. And to understand why that is, and why it matters, we have to go back in time. We have to understand the world before our world. Before the age of AI, before the internet, before the personal computer, there was a problem, a fundamental problem of computation. In the 1940s, the pioneers of computing were building the first electronic calculators. These were room-sized behemoths of vacuum tubes and relays, clacking and whirring as they crunched numbers for military ballistics or census data, and they were all wrestling with the same core challenge. How do you organize a machine to perform a series of logical steps? How do you create a universal architecture for computation? The answer, the blueprint that you are using to listen to this podcast right now, came from the brilliant Hungarian-American mathematician John von Neumann. In 1945, he outlined a design that was so elegant and so powerful it has remained the dominant model for computers for over 75 years. It's called, appropriately, the von Neumann architecture, and its core idea is a separation of powers. In this design, there are two distinct, physically separate parts of the computer. There is the central processing unit, or CPU, which is the brain of the operation. It's where all the calculations happen, the logical decisions are made, and then there is the memory. This is where the data and the instructions for the CPU are stored. Think of it this way. Imagine a library. This library contains all the information in the world. In the center of the library, sitting at a big desk, is a single hyper-fast librarian. This is your CPU. The library shelves, filled with books, are your memory. Now, let's say you want to solve a problem, like calculating a complex equation. The instructions for solving the equation and all the numbers you need are written in various books on the shelves. To solve it, the librarian has to get up from his desk, run to a shelf, grab the first instruction book, and run back to his desk to read it. The instruction says, get the number from book A, so he runs to another shelf, grabs book A, runs back, reads the number, and writes it down on a notepad. Then he checks his instruction book again. Now get the number from book B, so he runs across the library, gets book B, brings it back, and writes down the second number. Then the instruction says, add the two numbers together. He does that calculation at his desk. Then he runs back to put book A and book B away and get the next instruction. This is, in a simplified sense, how every computer, from your laptop to your smartphone to the massive servers in a data center, works. The processor, the librarian, is constantly fetching instructions and data from memory, the library shelves, and bringing them back to its desk to work on them. It does this millions, even billions of times per second. It's an incredibly effective system. But do you see the bottleneck? The single biggest limiting factor in this entire process is the physical distance between the librarian's desk and the library shelves. No matter how fast the librarian is, he still has to spend most of his time and energy just running back and forth, back and forth. This constant shuttling of data between the processor and the memory is known as the von Neumann bottleneck. For decades, this wasn't a huge problem. Engineers just made the librarian faster and the path to the library wider. We made processors that could calculate at gigahertz speeds and memory systems that could deliver data more quickly. We brute forced our way past the bottleneck, and it gave us the digital world we have today. But then, AI came along. And AI is different. Running a massive neural network isn't like a simple calculation. It's like asking our single librarian to read every book in the library, compare them all to each other, find hidden patterns, and then write a new book summarizing his findings. The amount of data shuttling required is astronomical. And this has led us to the quiet crisis I mentioned earlier, the AI power crunch. The data centers that run these large AI models are consuming an almost unbelievable amount of electricity. A single AI training run can consume as much energy as 100 U.S. households do in an entire year. By some estimates, within the next decade, the IT industry could be consuming 20% of all the world's electricity, with AI data centers being the primary driver. We are hitting the von Neumann bottleneck at a civilizational scale. The architecture that gave us the modern world is now threatening to limit its future. The problem was no longer about making the librarian faster. The problem was the library itself. We needed a new design. And for that, a few pioneering scientists began to look not at engineering textbooks, but at biology. In the 1980s, a visionary engineer at Caltech named Carver Mead started looking at the von Neumann architecture, and then at the brain, and he saw a fundamental disconnect. He saw the inefficiency of a system that separated processing from memory. He looked at the brain and saw a system where they were intimately intertwined. He realized that nature had solved the bottleneck problem billions of years ago. So he asked a question that was both radical and profoundly simple. What if we built a computer chip that was structured like the brain? He coined a term for this new field, neuromorphic computing. Neuromorphic simply means in the form of a neuron. It was a declaration of intent. Stop building faster librarians and start building a better library. So let's open the box. Let's place the von Neumann architecture and the brain's architecture side by side. We have our first analogy, the single superfast librarian running back and forth in a vast library. This represents the traditional computer. The processor is separate from memory. It's a sequential system. It does one thing at a time, just very, very quickly. It's like a single-lane highway. You can have the fastest car in the world, but you can still only move so much traffic. Now, how does the brain solve this problem? The brain doesn't have a single librarian. The brain is the library. Imagine a library with no central desk. Instead, next to every single book on every single shelf, there is a tiny specialized librarian. And all these thousands, millions of tiny librarians can work at the same time. If you need to compare book A and book B, the librarian standing right next to those books talk to each other directly. They don't need to run across the room. If you need to find a pattern across 1,000 different books, all 1,000 librarians can look at their assigned book simultaneously and report their findings in parallel. The processing, the librarian, and the memory, the book, are collocated. They are woven together into a single, massively parallel fabric. This is the first principle of neuromorphic computing. It is an attempt to physically build computer chips that merge memory and processing. On a neuromorphic chip, you don't have a big block of processing over here and a big block of memory over there. Instead, you have thousands of tiny, simple processing units, the artificial neurons. And each one of these neurons has its own little bit of memory built right in. It's a distributed parallel system, just like the brain. The single-lane von Neumann highway becomes a city with 1 million interconnected streets. This is also where we must address the most common misconception about artificial intelligence. When you hear the term neural network, today, you're hearing about a piece of software. It's a mathematical model that is inspired by the brain's structure. But that software is being run on hardware that is fundamentally von Neumann. It's like trying to simulate the traffic of a bustling city using only a single-lane road. You can do it if your car is fast enough, but it's incredibly inefficient. You're forcing a parallel idea onto a sequential machine. It's a brute force approach. Neuromorphic computing flips this on its head. It says, let's build the city first. Let's build the hardware that is inherently parallel, inherently brain-like, and then run our AI models on that. The early neuromorphic chips developed by Carver Mead and his students were rudimentary, but they proved the concept. They built silicon retinas that could process visual information directly on the chip, just like a real eye, without sending a stream of pixel data to a separate processor. They built silicon cochleas that could hear and distinguish sounds. These were not just faster computers, they were a different kind of computer. They were designed for perception and pattern recognition from the ground up. The implications for efficiency are staggering. By eliminating the von Neumann bottleneck, by stopping the endless shuttling of data between processor and memory, neuromorphic systems can perform certain tasks using a tiny fraction of the energy. For tasks that AI is uniquely suited for, like pattern recognition, sensor data fusion, and real-time decision-making, neuromorphic chips aren't just a little bit better, they are orders of magnitude more efficient. We're talking about 1,000, even 1 million times less power consumption. For the same result, it's the difference between powering your AI with a whole power plant versus powering it with a watch battery. It's a paradigm shift. But even this, the radical redesign of the chip's architecture, isn't the whole story. The parallelism, the merging of memory and processing, is a monumental leap. It gets us from the single librarian to the library full of them. But there is another layer to the brain's efficiency, an unseen giant that makes its low-power operation possible. It's a principle that is even more counterintuitive and more elegant than the architectural change. It's not just about the structure of the neurons, but about how they talk to each other. And understanding this is the key to the deepest aha moment of all. To understand this next principle, we need to adjust our analogy. Let's think about how a traditional computer, even one running a sophisticated AI, processes information from the real world. Imagine you are trying to get a computer to watch a video and identify when a person enters the room. A conventional computer built on the von Neumann architecture processes that video like a movie. It looks at every single frame. Frame 1, no person. Frame 2, no person. Frame 3, still no person. It analyzes every pixel of every frame, 60 times per second, constantly burning energy, constantly running calculations, just to confirm that nothing has changed. It's a brute force method. It is computationally expensive and wildly inefficient. Most of the time, the computer is processing redundant information. The wall is still a wall. The desk is still a desk. But it has to check every time. It's like a security guard who is forced to stare intently at a security monitor 24 hours a day, never blinking, just in case something happens. 99.9% of his energy is wasted watching an empty, unchanging hallway. This is how digital systems work. They are driven by a clock. With every tick of the processor's clock, a calculation is performed, whether that calculation is meaningful or not. The brain does not work this way at all. Your neurons are not constantly firing and updating each other on the state of the world. In fact, most of your neurons are silent most of the time. They are incredibly lazy. A neuron only activates, it only sends a signal when it has something important to say. It waits until it has received enough input signals from other neurons to push it over a certain threshold. When that threshold is crossed, and only then, it fires off a single, short electrical pulse, a spike, and then it goes silent again. This is called a spiking neural network, or SNN. Let's go back to our security guard. What if, instead of having him stare at a monitor all day, we just installed a motion detector in the hallway? The motion detector does nothing. It uses virtually no power. It just sits there, waiting. But the moment someone steps into the hallway, it sends out a single, sharp alert, a spike. The system only wakes up and uses energy when there is an event, when new information has entered the system. This is the difference between a clock-driven system and an event-driven system. Neuromorphic computers are built to be event-driven. They work with spikes. This principle is called sparsity. Information in the brain, and in neuromorphic systems, is sparse in time and space. Things only happen when they need to happen. This is the secret to the brain's incredible energy efficiency. It's not just that the librarians are standing next to the books, it's that they are all asleep until a book suddenly changes its content. Only the librarian next to the changed book wakes up, sends a quick note to a few colleagues who might be interested, and then goes back to sleep. This has profound consequences for the kind of AI we can build. An AI running on a traditional clock-driven system lives in a world of snapshots. It analyzes a frame of video, then the next, then the next. An AI on a neuromorphic, event-driven system experiences the world as a continuous flow of events. It's a much more natural and efficient way to process information from the real world, which is, by its nature, asynchronous and event-driven. A leaf falls, a door opens, a ball is thrown. These are events, not frames in a movie. This spiking computation is what will allow us to build truly autonomous, low-power intelligence that can live out in the world. Imagine a self-driving car. Today, its computers are constantly processing massive streams of data from its cameras and sensors, burning kilowatts of power. A neuromorphic system would be mostly dormant, only spiking when a pixel in its camera detects a change. A pedestrian stepping off the curb, a brake light flashing on the car ahead. It would react to the flow of events in real time, using a tiny fraction of the power. Imagine a medical sensor in your body that can monitor your vital signs for years on a single battery. It wouldn't be constantly sampling your blood sugar. It would be an event-driven system, designed to only send a spike of information to your doctor when it detects an anomaly, a pattern that deviates from your healthy baseline. This is intelligence that is not confined to a massive, power-hungry data center. This is intelligence that can be embedded anywhere and everywhere, running for months or years on a tiny coin cell battery. It's a future where we move from a world of brute force computation to one of elegant, efficient, event-driven intelligence. So where does this leave us? We started our journey with the magic of an AI that can write poetry, a feat of computation so complex it feels alien, and yet so intuitive it feels human. We assumed this intelligence must be like ours, running on a machine that mimics the brain. But when we looked inside the black box, we found something else entirely. We found a design, the von Neumann architecture, that has powered our world for 3/4 of a century, but is fundamentally limited. We found a librarian, incredibly fast, but forever trapped, running back and forth, burning more and more energy as our demands grow. Then we looked to a different blueprint, the one inside our own skulls. We discovered a system built on a different first principle, parallelism, a world where memory and processing are one, where a million tiny librarians work together, eliminating the bottleneck. And just when we thought we understood the brain's efficiency, we found an even deeper secret, a principle of sparsity, of communication through discrete events, through spikes. We found a library where the librarians are mostly asleep, waking only when new information arrives, saving an incredible amount of energy. This journey, from the von Neumann architecture to neuromorphic computing, is a perfect example of what it means to reason from first principles. It's about questioning our most basic assumptions. The pioneers of this field didn't just ask, how can we make computers faster? They asked, what is the most efficient way to compute? And the answer wasn't in making the librarian faster, but in redesigning the library based on a working model that has been optimized by billions of years of evolution. Understanding this doesn't just demystify AI, it gives us a deeper appreciation for the sheer elegance of the natural world. The technology of neuromorphic computing is still in its early days, but it represents a potential path forward, a way to continue the incredible progress of artificial intelligence without consuming our planet's energy resources. It's a future that is not just more powerful, but also more sustainable, more elegant, and more aligned with the way intelligence actually works. It promises a world where AI can finally move out of the data center and into our lives in a truly seamless way, as silent, efficient, and ever-present partners. The goal is no longer just to simulate an imagination, but to build a machine that perceives, learns, and reacts to the world with the same astonishing efficiency as the one that is doing the imagining right now, inside your own head.
You've been listening to First Principles. Until next time, stay curious.